Hello, my name is Florian, and in this presentation I'm going to tell you all about the work that's been going on in upstream LLVM to improve code generation for small matrices in LLVM and Clang. And let's jump right in. In this presentation, I'm first going to share with you the original motivation for this project, which should put into context some of the design decisions we took and some of the focus of the initial implementation. Then I'm going to introduce the matrix types extension that we added to Clang, which allows users to express matrix operations in C and C++. Then we're going to switch gears a little bit and take a look at how the matrix operations are represented in LLVM-IR, how the matrix types extension gets lowered to LLVM-IR and subsequently gets lowered to vector instructions. And finally, we're going to take a look at some performance numbers to give you an idea of what kind of gains the matrix types extension can bring to user code. This project originally started roughly 3 years ago, and the original goal was to provide users with a high-level solution that allows them to write high-performance code that operates on small matrices. This kind of code is common in computer vision or augmented reality use cases, for example. So the original codes we looked at shared a few characteristics. So the code makes heavy use of matrix math on small matrices. And in this context, the context we looked at, small matrices were from 2 by 2 element matrices up to matrices with 16 by 16 elements. And the element types were mostly single and double precision floating point. Any solution would also have to be flexible enough to support code generation for expressions with varying shapes. So the approach needed to be flexible enough to support operations on square matrices, rectangular matrices, on any size between in our range. And the codes we looked at, they were using column major as a layout for the matrices, which is why we chose to use column major as the default layout on in both the matrix types extension in Clang and the LLVM IR support for matrices as well. We started out by looking at some of the user code that implements math primitives in C and C++, and we came across code that looked a little bit like this, where the user tried to be nice to the compiler and help the compiler to optimize the code better by unrolling the matrix multiplier, for example. Code like this mostly relies on the SLP vectorizer to achieve reasonable performance. And then another case of class of implementations were using loops to implement some operations, like the example on the slide for a matrix multiply, because at some point it's not feasible for the users to hand unroll everything. And this kind of code relies on slightly different passes for optimizations. So in this case, probably the loop vectorizer, the unroller, and some other passes. And if you optimize those operators in isolation, that's mostly fine. LLVM does a decent job of optimizing code like that. But once you start mixing and matching operators that are optimized by different passes, you end up with some suboptimal code, especially at the edges where those expressions interact. For example, because you have to introduce additional spill code between operations, or say if the operators were optimized with different vectorization factors, then you might need some extra conversion code between the values. Our solution to this problem was to add matrix type support in LLVM and Clang. And we had a few key goals for this implementation. First, we want to guarantee vector code generation for matrix operations, and not just for independent operations, but for an expression tree of matrix expressions. That should help to better remove unnecessary memory accesses to temporaries. And finally, the extension should be user-friendly, so it's easy to use and the users are not tempted to try tricks to help the compiler. So for Clang, we added the matrix types extension for C and C++, which allows the user to express matrix operations in C and C++. On the slide, you can see an example program that uses the matrix types extension to load two matrices, two 4x4 matrices, then multiply them, add a scalar, and then store the result. Now, let's break things down a little bit. So the extension provides a way to define matrix types using the matrix types attribute. This attribute takes the number of rows and number of columns as arguments. And this is very similar to the X vector type in Clang, for example. And the matrix type is basically an extension to another dimension. Once we have our types, we also provide operators for those types. Currently, there is the addition, subtraction, and multiply operators. Addition and subtraction are element-wise operations, and the multiply is the matrix multiplication. In addition, there is a element subscript operator, which allows to access a specific element in a matrix given row and column indices. And then there is a set of built-ins to provide additional functionality. There is a built-in to transpose matrices. There is a built-in to store matrices to memory with a user-specified stride. And there is a built-in to load matrices of a specified size with a user-defined stride between columns. This extension is specified and documented as part of the Clang documentation and can be viewed online or in the LLVM repository. Now let's take a look at how things get lowered to LLVM IR. So our column major load built-ins, they are lowered to corresponding LLVM intrinsics that do column major loads. The math operators are also lowered to LLVM intrinsics for the multiply, and then to LLVM add vector instructions for the scalar or element-wise add. And in a similar fashion, the store built-in is lowered to the column major store intrinsic on the LLVM side. And okay, now let's break this down a little bit further. On the LLVM side, the matrix values are embedded in one-dimensional vectors in LLVM IR. So our 4x4 matrices that we had on the C++ level are represented as 16-element vectors in LLVM IR. This conveniently allows us to reuse the existing LLVM vector instructions for element-wise operations. So for example, our element-wise addition can be lowered directly to an LLVM fadd instruction. And for scalar operands, we can just use scalar LLVM vector constants. And then there is a set of intrinsics for operations that require shape-dependent information. And so those intrinsics take the dimensions of the matrix they operate on as arguments. So for example, our column major load intrinsic takes the dimensions of the matrix that it loads. In similar fashion, the matrix multiply intrinsic takes the shape of the arguments that it operates on. Now let's take a look at how those operations are lowered to LLVM IR, or rather lowered to LLVM vector instructions. This happens in the lower matrix intrinsics pass, which takes care of replacing the LLVM matrix intrinsics with corresponding LLVM vector instructions. The first step of the lowering is to collect and propagate shape information from the LLVM matrix intrinsics, and then propagate it to other instructions. We start by iterating over all the instructions in a function. And so we first visit the column major load intrinsic. And from the arguments, we know that we're going to load a 4x4 matrix. So we mark our matrix value as being a 4x4 matrix. Then we visit the matrix multiply intrinsic next. Again, we take a look at the arguments. We see that both input matrices are 4x4 matrices. Hence, the value produced is also a 4x4 matrix. Next, we visit the fadd instruction. The fadd instruction doesn't directly have any shape information, but it operates on an argument that has shape information that we found earlier. So we know the value 0 is a 4x4 matrix, and hence the result of the fadd will be another 4x4 matrix. So we mark our value 1 as also being a 4x4 matrix. And we continue that for all the instructions in a function. And once we have this information, we can start with lowering our instructions with shape information. And the idea here is to break down the operations with shape information that operate on matrices into LLVM vector instructions that operate on a single column. And this allows us to have a general lowering that works for each backend. So we start out with our column major load, which we're going to break down into 4 separate loads, where each load loads a single column, and we emit the necessary address computations using the user-specified stride as well. Next, we lower the matrix multiplication intrinsic, where we emit a series of shuffle vectors to extract the elements of the column we operate on, then multiply, add them, and move the results in vectors again using shuffle vector. Next, we lower the fadd instruction. The fadd instruction is already a legal LLVM instruction that we not necessarily have to treat specially, but we can make use of the fact that we know that the input operand is a 4x4 matrix, and the producer will create those 4 column vectors. So we can split up our FAD to also directly operate on those column vectors, which means that we don't need any extra instructions to convert the input operand back to a larger vector. And then similarly, for the store intrinsic, we just have to emit 4 vector stores, 1 for each column, again with the necessary computation of the addresses. And this means we can lower the complete original program without needing any conversion code in between. Besides this general lowering, there are a few other features that are also supported by this matrix lowering path. First, we also support tiled code generation for matrix multiplies. So instead of effectively unrolling the matrix multiplication completely, we can generate a tiled loop nest that performs the matrix multiply operating on a specified tile size. And it's also possible to have specialized code generation for specialized hardware extensions that provide instructions suitable for matrix operations. The example on the slide here shows how AH64's dot product instruction can be used to lower matrix multiply efficiently for hardware that supports this extension. But this could be extended to support arbitrary hardware extensions that provide specialized instructions for matrix operations, which has become more and more popular recently. Now that we know how things look in upstream LLVM now, let's take a look back at the original proposal that was shared 2 years ago. There are a few key differences, and the main difference is that it added a dedicated matrix type to LLVM-IR. So in our example, we would specify in our example, the code would operate on matrix values directly in LLVM-IR. And then for all other operations, intrinsics would be used. This has some advantages. For example, the intrinsics don't need to encode the shape information directly as arguments, so it's a little bit more concise. But after some discussion on the mailing list as part of the RFC, a few disadvantages of this proposal also emerged. So for example, by adding a new type, this also means that you have to teach various places in the optimizer about this new type. Otherwise, you'd miss out on very important optimization. One example is the scalar replacement of aggregates paths that would need to be taught to handle those new types. And you also have to thread this type through many places throughout LLVM, including the IR parser, the bitcode, readers and writers, and a bunch of other places. So you end up with lots of small changes across a wide range of files, and this was a constant source of merge conflicts when we kept our downstream implementation up to date with LLVM. And you need to specify some syntax for stuff like matrix constants, which you get for free by using the vectors. So this proposal was originally shared in 2018, and then after we received the feedback mentioned earlier, we went back to the drawing board and came up with this updated proposal using LLVM vectors and intrinsics, and shared this RFC roughly 1 year ago, and it has been accepted and is now part of LLVM. And similarly, on the Clang side of things, we worked with the Clang community to come up with a complete draft specification for the matrix types extension with documentation. And this landed a few months ago, and the implementation is almost complete. Now, to wrap up things, let's take a look at some of the possible performance gains from using this matrix types extension. And for that, first, let's take a look at a simple matrix multiply and accumulate. And we compare the matrix types extension to Eigen, which is a C++ matrix library. And the only difference in the source code is the type with which we instantiate the template. So for the Eigen version, we use the Eigen matrix type, and for the matrix types extension, we just use a type defined with the matrix type attribute. When running this on ARM64 for various sizes, we get the following results. What's shown on the slide is the change of the runtime of the matrix type version compared to Eigen. And positive values means Eigen outperforms the matrix types extension, and negative values means the matrix types extension outperforms Eigen. Let's take a look at some of those numbers. So first, we can see some, like a regression, and the case where we perform roughly equal to Eigen. So there's definitely still potential to tune some of the codegen for the matrix types extension. In this particular case of the 3x3 floating point case, the problem is that on AH64, we have vector instructions that operate on 2 floats and on 4 floats. But the way we lower it means that we, at the moment, we generate LLVM vector instructions operating on 3 elements, which cannot be efficiently lowered. So there's potential to improve things here. But then once we get to bigger sizes, we see more improvements by the matrix types extension up to 16 by 16, where we see the most substantial gain in this case. Now, oh yeah. So one thing to note here is that the goal of this extension is not to replace specialized libraries, but to give authors just an additional set of tools to write those high-performance libraries. Now let's take a look at some of the code generation and where the performance differences come from. For that, I'd like to take a look at the 4x4 double case, and I'll show you the assembly that's generated. The details are not really important, but I'll point out some key differences. So for the matrix types, we basically load all the operands up front, then we perform the computations using vector instructions, and then we just store the results. So there are no unnecessary instructions in between. If we take a look at the Eigen version, we load some operands up front, then we perform the multiply in a loop, and we can see that we have some loads that in here that don't use the full available width of the load unit, which is a problem. And then when we do the add, we have some additional reloads of the operands, which also adds unnecessary overhead and explains some of the differences. If you take a look at a more complex expression where we have a few multiplies, a transpose, and an add, we can see that the matrix types extension provides substantial gains as well. And if we take a look at the assembly differences here, we see a similar picture for the matrix types extension where we have some loads up front and a few instructions to transpose the values. Then we have mostly compute code with a few loads in between to load some additional operands. Now, if we take a look at the Eigen side, we note that we have again some single vector loads which don't make use of the full width of our load unit that are spread throughout the code. And then we also have some cases where we operate on 2 floating point values instead of 4 floating point values, which AH64 has dedicated instructions for. Now, to wrap up, So now everything I showed you so far is what's implemented currently in upstream LLVM and Clang, but there's potential for further improvement still. So we want to continue working on improving code generation for operations on larger matrices, especially better support to splitting up operations on large vectors. We want to improve and generalize the tiled loop code generation, finish up row matrix support, and improve some things in Clang, like initializer syntax and how fast my flags are handled. And of course, we would be more than happy to work with anyone interested in improving the matrix support in LLVM and Clang. And that brings me to the end of my presentation. Thank you.
Thank you, Florian. That was a really great presentation. I think an impressive amount of work from the language extension, the front end, all the way to the back end and code generation. Well done. We have quite a few questions, so let's start with that one. The first one is about the language extension, and the question is the biggest deployment challenge of this work acceptance of the extension? Is this work being proposed to the standardization committee, and are you looking if the GCC committee is willing to accept this work?
Yes, so that's certainly a challenge for deployment on platforms where Clang is not like the only or main compiler. But so currently my main focus is still on making sure that the implementation on the Clang side is finished, hopefully by for the next release of LLVM. And then I'd hope to get some people using it outside of the initial use cases we focused on to make sure that it works well for a wider range of use cases than the one we originally designed it for. And then hopefully see how that goes, and with more feedback from other users, go forward and see whether we propose it for the standard committee or at other places. And for the introduction, I just want to mention that all this work was not done by myself alone, but there were quite a few people involved internally working on this for quite a long time.
Yeah, thanks. So a little bit more specific then, the next question, you mentioned small matrices in your introduction and motivation and gave examples of 2x2 and 2x8 matrices. Can you elaborate a little bit what exactly are small matrices, and are there any kind of restrictions on the current implementation, and how well would it scale for bigger matrices? Can you elaborate on that?
Yeah, so I mean, we were mostly focused on matrices where the inputs fit directly on the available vector registers. So for AH64, probably like 8x8, 4x4, and up to 16x16. I think some of the benchmark numbers show that we ran show it works also well for slightly larger matrices. So 32x32 is something we tried, and also larger ones. And conceptually, there is no limitation on the size of the matrix. So you can, with the implementation that's available in Clang and LLVM, you can write use the extension to multiply matrices with 1000 by 1000 elements. But there is a problem when it comes to the lowering of that. So on the Clang side, it's fine. It will get lowered to the intrinsics. We can also lower the intrinsics, but then the way we do it is we break operations at the moment mostly down in operations on columns. So you'll end up with a lot of operations, say, with vectors that have 1000 elements. And this is something that LLVM, especially in the backend, does not handle very well. So you can write it, but it probably will take maybe 10 hours, maybe 20 hours to compile. But so this is where the limitation comes in. But we started already to work on a way to, instead of doing this naive lowering where we unroll everything basically, to generate a tiled loop nest to make it scalable for larger operations.
I think the next question is related. The usage of Clang vector and matrix type is limited due to the lack of compile time constant, length of the vector, or the number of rows and columns. Any thoughts on that?
I think that's related to kind of inquiring the number of rows and columns, for example, of a matrix type in C and C++. And that's something that indeed is not implemented at the moment, mostly because we are not unspecified, also not specified. Because that's something we didn't really use or need for our internal use cases. But this is exactly the thing I mentioned earlier, that we'd like to get feedback on what other people would find useful, so we can evolve the specification and make sure it covers, is as flexible as needed, basically.
And it looks like this is also related. And the next one, you, as you mentioned, you encourage contributions from others. What would your suggestions be where people can best start? Is that just by running code or fixing bugs, or what kind of contributions are you hoping for?
So, I mean, there are possibilities for contributions basically on each level. So, and also with different complexity. So, for example, on the Clang side, there are parts of the specification that are not implemented yet. For example, the compound assignment operators or casting between matrix types. So this is something where people could get involved in. Then there are other things in the specification that are not yet specified. So for example, there's at the moment no constant initializers for matrix types, which is something that would be really, really useful. This is something where people could contribute. And then on the LLVM side of things, there are is more tuning for the existing code generation we have. So on the slides, there was this example where we're not doing a terrific job when the size of the columns is smaller than the available vector width. So this is something to tune. And of course, this tiled loop code generation and target specific lowering, other things. I've created an umbrella issue on Bugzilla, which I'll link to this question, which is where people can find out more. And they can also reach out to me directly if they are interested.
Okay, next one. Next question, is there an option, ability to change the matrix layout from column major to row major, or does this need to be column major?
So on the Clang side, there's currently no way to change it, but it probably would be quite easy to implement that. On the LLVM side, there is actually a flag that you can change the layout that's used during the lowering between row major and column major. Mm-hmm. This is another thing where people, if they really love row major, then this is something I would be happy to collaborate on.
Yeah. And then the next question, I think we also chatted about this briefly on the LLVM dev list. Next question is the matrix multiplication restricted to the accumulation in the same types as the type of the coefficient of the operands? If there's no restriction, how is this decision made?
So I think, so at the moment, the size or the width of the element types of the inputs always have to match the outputs. But we discussed on the mailing list whether it might be useful for some use cases or to lower efficiently to some specialized instructions to have the input operands with a narrower type and then the result with a wider type. So this is, again, another feature that would probably need a small extension to the draft specification, but in the lowering itself, it should be relatively easy to implement, and then the lowering itself should also be possible without too much work.
Okay. The next question is about larger matrices. Have you considered integration with existing libraries such as BLAS and its various derivatives?
So this is something we explored. So instead of generating the code ourselves for large matrices, just generate calls to various libraries. So this is certainly a thing to sidestep the scalability issue for larger matrices as well.
Yeah.
I think that was the last question.
Yes, I think we're also out of time soon.
Yeah. Okay, well, that's good time.
Again. Thanks for all the questions, and thank you again, Florian, for the great presentation. Cheers.